Today we are actually going to start with the image processing, and we are having the hands-on session part 2. Then we will be having a brief introduction to signals, and the coding part of the signals I am giving you as an assignment. Okay, so that you have to do it. Okay, so then you can actually understand how an external library can be utilized for a particular thing. Okay, computer vision and image processing part. So computer vision is actually another branch of artificial intelligence. Okay, and there are different use cases for computer vision. So particularly in any device like IoT or any other mobile phone, any device, there is a vision based sensing technique, mostly with phones, cameras, and other image acquisition devices are there. And most of the data after collecting from these devices are actually processed using image processing and computer vision. Okay. So people are actually getting confused regarding this computer vision and image processing. People actually don't know whether I am doing an image processing technique or whether I am doing a computer vision task. So the first thing we can actually understand what is a computer vision and what is image processing and how they are connected. Okay. So usually digital image processing is the use of digital computer to process digital images through a algorithm. Okay. So digital image processing is a branch which is particularly coming under signal processing. Okay, signal processing, digital signal processing, and it utilizes digital computers to process digital images through algorithms. Okay, so it is actually viewed as a field of digital signal processing. And keep in mind, in digital image processing, the input will be an image. Okay, the input will be an image, and the image will get manipulated using an algorithm, and the output of that particular process is again an image itself. Okay, so the original image, it is getting processed, and we are getting the processed image as an output. Okay, so what is a digital image? A digital image, as you can see, so this is a digital image, right? An aerial image. So if you zoom that aerial image, you can actually see a collection of square blocks. Okay. And that collection of square blocks are particularly called as what? A pixel. Okay. Collection of pixels. So a pixel is the unit uh, element which holds an information within an image. Okay. So an image, a digital image can be viewed as a rectangular grid of pixels. Okay. So here we can see a grid. There are 5 rows and 5 columns, and each of this element in the grid is actually possessing a particular information, a color information, and that is what we are calling as a pixel. Okay. So here we can see that here we have 6 rows and 6 columns. Each one is actually showing some kind of shades of gray, right? Corresponding to that, we have a matrix. So usually an image is represented as a matrix of pixels. Okay. So what is a pixel? A pixel is the pixel in pixel, a point or cell in the image that contains a color data, and each pixel is made up of bit, and how this is actually formed, how a pixel is actually getting formed. So before understanding the representation of pixel, we have to understand there are usually three different types of images. Okay, the first one is called as binary image. The second one is called as grayscale image, and the third one is called as color images. Okay, so in binary images, as you can see, there are only two different levels of intensities. The one intensity is black and the other intensity is white. Okay, so a pixel can hold either two intensities, black or white. But in the grayscale image, apart from this black and white, you can actually see a lot of other shades of black and white or other shades of gray. So that is why it is called as a grayscale image. And in color images, we can actually see the color colors that formed using different primary colors or secondary colors. Okay. So how these things are actually getting represented. So in the case of binary images, as I said, each pixel can hold either a high intensity or a low intensity. And the high intensity is represented as 1 and the low intensity is represented as 0. In this example, it is actually interchanged, like the low intensity is represented as white and the high intensity is represented as black. Okay. So it can be vice versa too. Okay. So whatever it is, see a single pixel, okay, a single pixel is actually represented using what? A single bit. Okay. Because a single bit can either have value 0 or 1. And this 0 represents black usually and 1 represents white. This is the logic. So 1 pixel is represented using either 0 or 1, right? And to represent 0 or 1, we only need 1 bit. Okay, 1 bit. Okay, that 1 bit can be either 0 or 1. So if you have an image of size 100 by 100, what will be the size of that image in bytes? Can you tell me? Anyone? If an image is represented using a grid of 100 by 100, what will be the size of that image if it is a binary image in bytes?
25, sir.
How much?
25.
25. How did you get that? 25.
10,000 by 8.
Yes, that is the correct value. Like, and how we can actually get that? See, if you have 100 by 100 image, what do you mean by 100 by 100 image? There will be 100 rows and 100 columns, right? So, how many pixels are there? What is the total number of pixels? What is the total number of pixels?
10,000.
Yes, 10,000 pixels are there. Okay. And for representing 10,000 pixels, how many bits are needed? For
10,000 bits because 1 bit for each.
yeah, 10,000 bits are needed. And we know 1 byte is equivalent to 8 bits, right? So how many bytes are there? 10,000 by 8. Is that clear?
Yes.
Is it clear?
Sir.
10,000 by 8 bytes is actually needed for representing this image. Hope it is clear, right? Everyone?
Yes, sir.
Yes. Now, moving into grayscale images, the grayscale images are actually having more than one level, sorry, 2 levels of shades. Okay. So in binary images, as I said, we can have only 1 bit per pixel, and that 1 bit can be utilized for representing either 0 or 1, right? But suppose we are having 2 bits to represent a single pixel. What are the possible values we can actually hold in that? It can be 0, 0, 0, 1, 1, 0, or 1, 1, right? So how many levels we can actually represent? How many levels of intensities we can actually represent using 1 pixel? 1 pixel can be either
4.
in 0, 0 or 0, 1, 1, 0, 1, 1. That is 4 levels, right? So this 0, 0 will be the black. Okay, the core black. And 1, 1 will be white. In between, we can have different shades of grays. Are you getting it? Are you getting it? So
We have
for
only 4 levels, right?
we can have 4 levels, and one level is the 0, 0 level is represented as black. The 1, 1 level is represented as the pure white. In between, 2 different shades of gray, like this. 1, 2, 3, 4.
Okay, okay.
Okay. So with 2 pixels, I can represent how many levels? 2 raised to 2, which is equal to 4 levels, right? So what will happen if I use 3 bits for a pixel? It can be either 0, 0, 0, 0, 0, 1, 0, 1, 0, likewise 1, 1, 1, right? So how many levels will be there?
8.
8 levels will be there. And each one is, this is actually the core black and this is the white. Then in between there are 6 gray levels are there. Is it clear?
Yes.
Right? So if you have n bits to represent, if you have n bits to represent a pixel, then you can have 2 raised to n different levels of gray. Okay, 2 raised to n different levels of grays. And in most of the time, we use grayscale images with 8 bits per pixel. Okay, 8-bit grayscale images are usually in use. Hope this is clear, right? So if you are using 8-bit grayscale image, how many levels you can actually have?
2 raised to 8.
Yeah, 2 raised to 8. 2 raised to 8 is starting from 0 till 255. There are 256 levels, and the first level is 0. The last level is 255 itself. Hope it is clear, right?
Yes, sir.
Yes. And now, can anyone tell me what is the size of the image? Size of the image. Size of the image having a dimension of 120 cross 120 with 8-bit representation.
2 raised to 8 into 120 into 120.
Again.
2 raised to 8 into.
What is the need of 2 raised to 8? So if you have a 120 into 120 image, total number of pixels? 120
120
cross
into 120, that is 14,400.
400.
Then we just divide it by 8, that is 1,200 and something. 1,800. Am I correct?
Again. Total number of pixels. Total number
It
of.
would be 8 into 128 into 128.
Yeah, total number of pixels is 120 cross 120, right? Then each pixel need 8 bits. Each pixel need 8 bits. So total number of bits?
8 into 128 into 120.
8 into 128 into 120. Right? 120 into 120. Then number of bytes?
128 into 128.
120 into 120. That is 14400 bytes are there. Is that clear? And if they are asking for kilobytes, you have to divide it with 1024 2. Yes. Now, the case of color images. The color images are actually represented using different color spaces. Okay. The common color space we are actually using is RGB image. Okay, RGB image. That is every color. Okay, every color can be a superposition of three different primary colors, which is red, blue, and green. Okay, so when whatever color you have, this will be a combination of different intensities of red, blue, and green. So a single pixel is actually composed of red, blue, and green, where the red can have a representation with 8 bits. The blue can also have the representation with 8 bits, and the green can also have the representation between the representation with 8 bits. So each R can have an intensity value between 0 to 255. This is also 0 to 255. This is also 0 to 255. Okay. So a single pixel is always represented as a tuple that represents a value 10, 20, 37. So this is the intensity of red, this is the intensity of blue, and this is the intensity of green. So the black color is actually represented as all the intensities are low. That is 0, 0, 0. And the white color is actually represented using all the intensities are high. That is 255, 255, 255. Hope it is clear, right?
Yes, sir.
Yeah. So the yellow color, we know yellow color is actually a combination of what? Red and green, right? So can you tell me what is the representation of yellow?
255, 255, 0.
255, 255, 0. Yes. The high intensity red, the high intensity green, and blue is absent there. Okay. Hope it is clear for you. Everyone, is it clear? So this is the representation of colors. Then in image processing, what all things we can actually do? I'm just going through these things in a very quick manner. See, the image processing, the first one is actually called as filtering. The filtering is nothing but it is actually enhancing the image. And we are actually going to discuss filtering in a detailed way. Then image watermarking. The watermarking is actually embedding a text into an image. That is what we are calling as watermarking. Then compression. The one image is actually reduced into a particular size. And this is what we are calling as morphological operations. We are actually going to discuss on that in detail way, the morphological operations. Okay. And this is what we are calling as edge detection. This is a foggy image. After enhancement, we can actually see the image in this way. This is what we are calling as image enhancement. This is actually histogram. Histograms are actually going to discuss in a detailed way because we are actually having the practicals of histogram. Okay. So histogram is nothing but, see, we know how each pixel can be in the range of what? 0 to 255, right? So in the x-axis, we will keep 0 to 255. In the y-axis, we will count the number of pixels each intensity is having. That representation is called as what? Histogram. And histogram equalization is a process of equalizing the distribution of pixels over different within a particular image to follow a normal distribution. Then image transformation we can actually do from one particular domain to another domain. then image restoration, image reconstruction, image super resolution. So for every task related to image processing, you can see that one input image is there, and that input image is actually transformed into another image with the help of a particular process, and that process is actually realized using a particular algorithm. Okay. And computer vision is again a confusing domain we always interchangeably use with this image processing. So computer vision is not actually equal to image processing, but we can say that computer vision uses image processing, and sometimes image processing also uses computer vision. Okay, so computer vision as a field of AI that trains computers to understand, interpret visual world. Okay, so this is how the human vision system works, right? We have a sensory organ, our eyes, and that eyes are actually uh, getting the inputs or perceiving the inputs to as visuals, and that signals are actually transferred into brain, and the brain is actually processing that, and from that processing we are actually able to understand that visual, or we can actually get the information from the visual, right? We can interpret that visual, like different things are actually happening. Similar to that human vision system, in computer vision, we have any of this acquisition or sensing device. It can be a camera, or it can be a CT scan image, a CT scan machine, or an MRI scan machine, or it can be a radar, sonar, whatever it is. It is a sensing device, and that sensing device will capture the visuals, and it will get processed by a computer which do the equivalent part of brain, and with the help of computer vision algorithms, and we will get the semantics, syntax, or any other visual interpretation of that particular input. Okay. So the core difference is image processing. It's a research area within signal processing, focuses on syntax, low level features, and image is converted to images. But in computer vision, research area within a computer science or AI focuses on semantic, symbolics, or geometric description of the image. So image is actually getting transferred into object semantics, captions, or something like that. Okay. Hope it is clear, right? Everyone? Everyone, is it clear? Can you put a response on the chat box?
Okay. Sir,
Is-
could you please repeat it?
Yeah. So in the case of computer vision, in the case of image processing, we take an input image and we will apply that image into a particular algorithm. That algorithm will manipulate that image, and as a part of that, you will get another image as an output, right? So you are converting a color image to black and white, or you are enhancing one image into a clear one. All those things are actually what? Image processing. But in computer vision, instead of transforming one image into another image, we focus on getting the semantics, meanings, symbols, or anything interpretable, or any interpretations from the input visual to understand that image in a better way. Clear?
That
Yes.
semantic part, actually, that semantic usually,
Semantics is usually called as the meaning we are getting from the image. So I will show you one example for that. See, here OCR is a computer vision application where what we are doing is, if you have a bill like this, it will extract the text. Okay, it will extract the text from the bill, and you will get it as a text as an output. So this is not an image, this is the textual output. And the number plate detection is one example. Then face detection. This is what we are calling as semantics. That is, from the input, we are understanding that there is a smiling face. Okay, there is a smiling face in it. That we are interpreting, or we are perceiving the semantics of that particular image. And this is what we are calling as a smile detection. And the face recognition. Face recognition is nothing but identifying whose face is that. That is what we are calling as face recognition. Face detection is something different. We are actually focusing on where is the face. The face is actually getting localized with a particular rectangle. Okay. And vision based biometrics, and that what we are having as the iris based biometric devices and all, right? Then we can create special effects with computer vision. We can see the applications of computer vision in analyzing sport videos. Then we can see the overall brain of a autonomous vehicle is actually the computer vision itself. And in robotics and in medical imaging, like suppose you are having an image, a CT scan image or a X-ray image or an MRI image or whatever, PET scan or whatever it is, we can actually do computer vision, or we can actually perform computer vision methods to understand and diagnose the disease from that particular input. And how it usually works, the computer vision usually works by combining the image processing techniques along with machine learning or deep learning stuff. So as we know, the input will be there. Then we have to do a lot of pre-processing with image processing. Like we can make the brightness transformation, geometric transformation. We can do filtering, segmentation, Fourier transform kind of pre-processing techniques. Then based on the problem within the from the image, we can extract color features, we can extract edge, we can extract the texture based features, we can extract the shape based features, we can extract the wavelet, we can extract different other texture based features. A lot of things can be extracted as a feature engineering technique, then applied for a machine learning stuff. And the computer vision also get accelerated now by deep learning techniques. And with deep learning, we can do the image classification. On giving a particular image, we have to classify the image into a particular category. Okay, object detection from within a particular image, what all objects are present in it, and where is exactly the location of a particular object. That is what we are calling as localization. Semantic segmentation, exactly on which pixels a particular object. Here the object is the chair. Exactly where is the chair? That pixels are getting marked. That is what we are calling as segmentation. Then pose estimation, then landmark detection, then face detection, face landmark detection, object tracking. These are the different segmentation techniques for semantic segmentation. See, in an autonomous car, if you see a visual like this, the car is actually interpreting that visual like this. Okay, semantic segmentation. And it will also do the instance segmentation to find out all the instances. Then it will combine the semantic segmentation and instance segmentation to get a pan-topic segmentation. So there are a lot of things are actually happening. Then using computer vision, you can create a caption for a particular image. We can actually ask questions related to a particular image. Then we can create black and white to color image, a drawing to coloring it, then a foggy image to another one, right? A lot of things can be done with this computer vision. Okay, so we are not going to the details of computer vision in this particular bootcamp, but we will go through some of the techniques called classification kind of stuff with deep neural networks, and we will be having a thorough understanding of the basic image processing and the feature extraction techniques we are usually doing with images in the practical part. Okay. So that theoretical understanding is now clear for you, right? Is that clear? So you can actually load that Google Colab file I have shared with you. Image feature extraction. Okay. So after loading the image, you can upload that file that I have shared with you. In day 9, you can see a data.zip. Okay. Data.zip. So hope everyone loaded the file and data, right? Can I start or do I need to wait?
സർ ഒറ്റ മിനിറ്റ് ലോഡായിട്ടില്ല, ഒരു മിനിറ്റ്.
Okay, okay. Is there any blockers? Gaurav, are you able to load the file? For all others, ഇനി നമ്മൾ ചെയ്യാൻ പോകുന്ന കാര്യങ്ങൾ വളരെ കീനായിട്ട് ശ്രദ്ധിക്കുക. ചെയ്യാൻ വളരെ എളുപ്പമാണ്, നിങ്ങൾക്ക് മനസ്സിലാകാനും വലിയ ബുദ്ധിമുട്ടൊന്നും ഉണ്ടാവില്ല. ബട്ട് ഈ രീതിയിലായിരിക്കും നമ്മൾ ഡീപ്പ് ലേണിംഗ് ഉപയോഗിച്ചല്ലാതെ ചെയ്യുന്ന ഇമേജ് അനലറ്റിക്സിലൊക്കെ വരുന്ന സ്റ്റെപ്പുകൾ. ഓക്കെ, അപ്പോൾ എല്ലാവരും എന്ത് ചെയ്യുന്നു വെച്ച് കഴിഞ്ഞാൽ ജസ്റ്റ് ഒന്ന് മെഷീൻ ലേണിംഗ് പഠിച്ചു കഴിഞ്ഞാൽ ഒന്ന് ഡീപ്പ് ലേണിംഗിൽ പോകും, CNN ബിൽഡ് ചെയ്യും, നിങ്ങൾ ക്ലാസിഫിക്കേഷൻ ചെയ്യും, ഒബ്ജക്റ്റ് ഡിറ്റക്ഷൻ ചെയ്യും, ഇതെല്ലാം വളരെ പെട്ടെന്ന് പടപടേന്ന് കാര്യങ്ങൾ നടക്കും. പക്ഷെ ലേണിങ്ങിന്റെ പെർസ്പെക്റ്റീവിൽ ഞാൻ പറയുകയാണെന്നുണ്ടെങ്കിൽ ഡെഫിനറ്റ്ലി നിങ്ങൾ ചെയ്യേണ്ടത് ഈ പറയുന്ന രീതിയിലുള്ള ഫ്ലോ ആണ്. ഇതിൽ ഓരോ തരത്തിലുള്ള ഇമേജ് ഫീച്ചർ എക്സ്ട്രാക്ഷൻ ടെക്നിക്സ് ഒക്കെ മനസ്സിലാക്കി അതിന്റെ പ്രീ പ്രോസസിംഗ് ഒക്കെ മനസ്സിലാക്കി പോവാണെന്നുണ്ടെങ്കിൽ യു വിൽ ഗെറ്റ് ആൻ അപ്പർ ഹാൻഡ് ഫോർ ദിസ്. ഓക്കെ, സോ ഹോപ്പ് എല്ലാവരും
data.zip ആണ് അപ്ലോഡ് ചെയ്യണ്ടേ?
data.zip. പിന്നെ അത് 1 by 1 അപ്ലോഡ് ചെയ്യാൻ ബുദ്ധിമുട്ടായതുകൊണ്ട് ഞാൻ സിപ്പായിട്ട് നിങ്ങൾക്ക് ഡേറ്റ തന്നതാണ്. ഓക്കെ, so you can actually upload the zip. Then the first block of the program itself is unzipping that. Okay, unzipping that particular zip. Then you can see the input images here. കണ്ടോ? ഓക്കെ, ഞാനിപ്പോൾ ചെയ്യാൻ പോകുന്ന എക്സ്പെരിമെന്റ്സിലെ images ആണ്. So these are all images that I am going to utilize for this experiment. Okay, അല്ലേ? Are you able to see that?
അൺസിപ്പ് ചെയ്തത് എങ്ങനെയാ?
ഈ ഒരു കോഡ് തന്നെ എക്സിക്യൂട്ട് ചെയ്ത് കഴിഞ്ഞാൽ അത് അൺസിപ്പ് ആയി.
അതങ്ങനെ ആയിട്ടില്ലല്ലോ, കോഡ് എക്സിക്യൂട്ട് ആയി,
ആയിട്ടില്ല എന്നുണ്ടെങ്കിൽ ഇവിടെ ഒന്ന് റിഫ്രഷ് ചെയ്താൽ മതി. സോ വി ആർ ആക്ച്വലി ഗോയിങ് ടു യൂസ് എ പർട്ടിക്കുലർ പാക്കേജ് കോൾഡ് OpenCV. That OpenCV is already installed.
സോറി, എനിക്കത് ചെയ്തിട്ടും വരുന്നില്ല,
അൺസിപ്പ് ആവുന്നില്ല. മാം ഇത് അപ്ലോഡ് ചെയ്തോ?
data.zip എനിക്ക് കാണാം.
അത് കംപ്ലീറ്റ് ആയിട്ട് അപ്ലോഡ് ആയി കഴിഞ്ഞോ?
കംപ്ലീറ്റ് ആയിട്ട് അപ്ലോഡ് ചെയ്തായിട്ടാണ് മനസ്സിലാവുന്നത്.
ഇത് എക്സിക്യൂട്ട് ആയോ?
ഫയൽ അതെ ഇമ്പോർട്ട് ചെയ്തു.
അല്ല എക്സിക്യൂട്ട് ചെയ്തോ, റൺ ചെയ്തോ?
റൺ ചെയ്തു.
ഈ ഗ്രീൻ ടിക്ക് വന്നോ?
വന്നു.
ഓക്കെ, ഇനി മാം ഇവിടെ നിന്ന് റിഫ്രഷ് ചെയ്തേ.
ശരിയായില്ല.
വന്നിട്ടില്ല, ഇവിടെ കാണുന്നില്ല, ഡേറ്റ എന്നുള്ളൊരു ഫോൾഡർ കാണുന്നില്ല.
കിട്ടി കിട്ടി. ഓക്കെ വന്നു.
വന്നില്ലേ?
വന്നു.
Okay. Yeah. So all our inputs are there in the data folder. So the first experiment I am going to do is, see, ഇവിടെ നമ്മൾ OpenCV import ചെയ്തിട്ടുണ്ട്. Then we are actually using the function imread to load the image car.jpg. Okay. Then this is img is the image. Okay. So this image is actually stored as a numpy array. Okay. A numpy array, and that numpy array is actually storing pixels. Okay. And since it is a color image, each entry will be having 3 components. Okay. So we can see that. See, after loading this, I'm just adding an extra row here and simply printing that img. Okay. So you can see that, right? There are a collection of what? Pixels, and each pixel is having how many values? R, G, and B. Okay, RGB. Okay. So you can also look here thing. And on hovering on this IMG, you can see that, see, this is a numpy array. And what is its shape? 13642048, 3. What is 1364? Number of rows. 2048 number of columns, and each entry is actually having 3 components. That is why its shape is showing us 3. Okay. Now, to show the image, okay, usually what we will do is we will do this cv.show wait key and destroy all the window. Then the image will appear as a window. But since it is Google Colab, this will not get, that window will not get appear here. It will only display at the Google server. So there's a patch for that. That image coming in that window will be bypassed to our HTML page. And to do that bypassing, we have to use the cv2.imshow. Okay. So you can see the image over here itself. See? Okay, so this is the input image of the car. We have loaded this. Okay. Okay. Now you can write that car. So previously it is a JPEG image. You can see that this is a JPEG image. Okay. And while writing it, what I did is I converted that into PNG. Okay. PNG. And you can see that new image was saved here, car.png. Okay. So after processing, you can save your image using the imwrite function. Okay. Okay. Now, another way to read, to show that image is, see, here we are reading the image, then we use the matplotlib to show that. But while displaying this matplotlib, the orange car is actually interpreted as now blue one, right? Can anyone tell me what is the reason for that happening is, usually the matplotlib interpret a pixel value, that is the pixel value here, as RGB, right? But in OpenCV, by loading the image, the OpenCV is actually loading that images in the format of BGR. BGR. So what is happening is, the blue color is interpreted as red, and the red color will be interpreted as blue. And there won't be any change for green. So if there is any green, you can see that as it is. But here the blue is appearing because the orange color is now interpreted as the intensity of blue. Okay. So in usual case or in matplotlib, it is reading the image as RGB, but the problem is with CV, OpenCV. The OpenCV read the image in the format of BGR. Okay. Now cropping an image, how to crop it? For cropping the image, see, load the image using, this is another package called PIL. Okay, PIL, pillow. This is uh, also an image processing package. Here, the image is loaded as image.open. Instead of imread, we can use image.open. Then we can do the crop function here, im.crop, and we have to specify the bounding box left top corner, x and y, and the length and the width to be cropped. Okay. Then we can save that in the folder as cropped image. Okay. So if you load this, you can see the cropped image is actually loaded over here. Okay. Then this is the another way to crop. Instead of exactly specifying the xy coordinate and length and y, you can relatively give the position. Okay. So for the entire image, 1/4 of the width, 1/4 of the height need to be cropped out, and 1/2 of the width and 1/2 of the height. Okay. So from the 1/4, it will crop out the 3/4. 1/4 plus 1/2. Okay. So you can see that the center part is actually getting cropped from the input. And also you can do the transformation, the rotation transformation. You have to specify the 2D rotation matrix. Okay. And to get the height and width of the image, you can use the slicing operation from shape. img dot shape, that is actually giving three values, the length, width, and the depth. And from that, the first two, the height and width is actually taking. Okay. Then height and width is getting. Now you have to define a rotation matrix. Then here we are not only rotating it, we are making the length and width into its half. Right? Is that clear? Right? And the scaling is also done as 0.5. Then we will apply that rotation matrix on the input image, and the rotated image is actually showing here. And not only rotated, it actually scaled and translated. Okay. So the next two experiments is actually showing how the resizing can be done with the image. So this is what we are usually do from 0, 0 for the length. For the length, we have to reduce it to 0.25, and for the height, we have to reduce to 0.3. So if 100 is the width, it will get reduced into 25. If 100 is the height, it will get reduced to 30. That is the fraction we are specifying here. And directly we can resize by specifying the new size. So cv2.image resize of image comma 800 comma 600. Okay. Right. The resized image is there, and this is how an image is manipulated for writing something on that. Okay. So here, see, you can see an output sample text on image, right? And how this can be done. First, we have to load the image, resize it into 800, 600, then set the font. Okay, set the font CV2 dot font H3 simplex, then origin, where the text should be plotted. Scale, the font scale is 1. The color is 25500, that is the red color. The thickness of the font is actually 2. Then use the function put. So in the image, put the text, sample text on image at the origin and with the font size, a particular font, the font size, the color, thickness, and the line algorithm you have to use. So you can see this output. And if you simply change the color like this, and maybe the origin like this, you can see the difference, right? Now the the text is actually shifted right, and also the color is changed to green. So hope you have done the experiments so far. Can you just put an S on the chat box if you have done or if you have experimented so far? So is there any confusions in the input? Okay, fine. So the next is a very important topic, the color spaces. Okay, most of the image processing classes will not actually deal with this, but it is a very important topic. Okay, so as I said, in image representation, we use different techniques to represent a color image, different uh, mechanisms to represent a color image. So the usual one is RGB image. RGB image in the sense every color is created as a combination of red, blue, and green. Okay, red, blue, and green. So here you can see that this can be represented as a three-coordinate system. Here, this is actually the red, and this is blue, this green. Okay, right? Each corner is actually representing what each of the color, and together this point is red, and symmetrically opposite we can see the black. So every color will be on this particular cube. Okay. And there is another representation called as hue, saturation, and value. Here, a single color is actually a combination of or a what it can be decomposed into a value called hue, saturation, and value. The value represents the brightness. Okay. The saturation represents the color scheme. Sorry, the hue represents the color scheme, and the saturation represents the intensity. Okay. Okay. So every color can be a particular value, can have a particular value for hue, saturation, and value. And similar to that, there is something called lab color space. Light A and B axes are actually used to represent it. There, three components are actually representing the light intensity, the A axis, and the B axis. Okay. And again, the YCB, CRCB, that is another transformation. Here, RGB is actually represented or transformed into YCB-CR. Okay, YCB-CR. This is another representation. So we have particular use cases for representing each image in each color space. We can actually see that. Okay. So see how I am going to transform a particular image which is loaded in BGR to another color spaces. Okay. So this is one image called apple. Apple is here. See, this is the image apple. Okay. Now I am loading it, and that image is actually called as what? Image. Then that RGB, the BGR image is actually getting converted to RGB, The BGR to converted to RGB. So for that, you have to use the CVT color function, CV2 dot CVT color of image, comma, CV2 dot color underscore BGR to RGB. So now the image is converting, this image is converting from BGR to RGB, and it is stored in RGB. Then BGR to gray. BGR to gray is actually there. Then BGR to HSV. Okay, BGR to HSV, BGR to lab, BGR to YCRCB. So each image is stored as image, RGB, grayscale, HSV, lab, YCRCB, right? Then what we are doing is we are creating a matplotlib plot and plotting all these converted images as a single row. Okay, so you can see that, right? The original image in RGB, then the grayscale image, the HFC image, the lab image, and the YCP CRCB image. So using this, we can actually convert each image into different color spaces. Okay. So what is the peculiarity of this? Why we need to convert this? So by converting each image into one color space, we can actually get different information. Okay, we will get different information on that. Okay. Yeah. So here, what we are doing is, see, first we are loading the color image flower, then we are converting that BGR to gray. Okay. Then we plot and we convert that gray image after equalizing it into equalized gray. Okay. And you can see the difference. After histogram equalization, the majority dark is actually normalized into the gray. Okay. So this histogram equalization can enhance some images by avoiding the unwanted darkness into a clear information. Okay. And this is what we are calling as histogram equalization. Okay. Now we are actually plotting this equalized. See, we are taking the gray pixels as a gray flag and the equalized pixels as equalized gray flag. Then we are plotting the histogram for both of them. Okay. So after plotting, you can see how it looks like. See, in the first image, the majority of the pixels are actually near to 0, that is here, right? Okay, only few white images are there, white pixels are there. But after equalization, what will happen? Every bin is actually getting normalized. Okay, every bin is actually getting normalized. So this image is having a histogram like this, and this imaging is having a histogram like this. Okay, hope it is fine, right? So the usual need is to enhance the image by avoiding the unwanted dark patches within the image. Okay. And morphological operation is something, see, a very useful one. There is an operation called erosion. So before that, what I'm doing is I'm just loading an input image, the sample. Okay, you can see the sample. It's an image like this. Within a white background or a gray background, I am having a black test. Okay. So on loading that image, I'm specifying a parameter 0 here, right? That is to load that image into grayscale, right? So even if you load that in grayscale, see on plotting, you have to see a white color here and a black color for the text, right? But what happened here is, see, the image is actually manipulated like this. After loading, I am subtracting 255 minus image. So what will happen? Every pixel is actually getting subtracted from 255. So all 255 will be converted to what? All 255 will
0.
be converted to 0 and all zeros will be converted to what?
Minus 255, which actually 255.
No, not minus 255. 255 minus 0, it's 255
255.
itself.
Yeah, yeah.
itself.
Sorry.
Okay. So all blacks will be converted to white and all white will be converted to what? Black. Okay. And why we are seeing this purple and yellow? Because while plotting this image, the IM show interpret every black pixel as this purple and white pixel as yellow. So to change that, you can use this C map. There is an option called C map equal to gray. If you use that color map, you can see like this. Okay. Is it clear? Okay. So the image is loaded and inverted by subtracting that image from 255. Okay.
സർ ആ 255 മൈനസ് ചെയ്യുന്ന സെക്ഷൻ ഇല്ലെങ്കിൽ എന്താ സംഭവിക്കുക?
Yeah, if
ഒന്ന്
it is
നോക്കട്ടെ.
not there, എന്തായിരിക്കും സംഭവിച്ചിട്ടുണ്ടാവുക എന്ന് ആലോചിച്ച്.
അതിന്റെ നേരെ ഓപ്പോസിറ്റ് കിട്ടും അല്ലേ?
Yeah, the
Yellow
actual image എന്താണ്
background
അതുപോലെ
കിട്ടും.
തന്നെ കിട്ടും. ഓക്കെ അല്ലേ?
ഓക്കെ
സീറോ കൊടുത്തതിന്റെ ആയിരുന്നു.
ഈ 0 കൊടുത്തത് മാം, ഇത് ശരിക്കും ഇതൊരു കളർ ഇമേജ് ആണ്. ഇത് RGB വാല്യൂസ് ഉള്ള ഇമേജ് ആണ്. അതിനെ ഗ്രേ സ്കെയിൽ ആക്കി എടുക്കാൻ വേണ്ടിയാണ് നമ്മൾ ഇവിടെ എന്ത് കൊടുത്തത്? 0 കൊടുത്തത്.
സാറേ 255 മൈനസ് ചെയ്യുമ്പോൾ നമ്മൾ ആക്ച്വലി കളർ ഇൻവേർഷൻ അല്ലേ ചെയ്യുന്നത്?
അതെ കളർ ഇൻവേർഷൻ ചെയ്യുന്നത്. എക്സാക്ട്ലി. Okay. Now we have an operation called erosion here, right? First, actually see the result of erosion. After doing the erosion, what happened here is the width of the image is reduced, right? So what is erosion? In erosion, what we are doing is, this is a very important operation. See, in erosion, suppose we are having an image. You can see this, right? See the screen, right?
യെസ്.
Okay. So we have something like this, an input image, and okay. Okay. So suppose we are having a shape like this. Okay. These pixels are red. Okay. So these pixels are actually the black, the other one is white. Okay. Now, while doing the erosion, we will be having a structuring element. What is that? We'll be having a structuring element. So the structuring element can have any shape. It can be like this, okay, or it can be like this. So this, say this is our structuring element. What we will do is, we will place the structuring element at this point. This point, this point, this point, everywhere we will what? Place the structuring element, okay? So at this point, the structuring will be like this, right? This is the overlapping, right? But this is not completely overlapping, only these two pixels are getting overlap with the actual one, right? Right, actual one, right? So then we will place here. Then also these three will be overlapped. When we place here, these four will be overlapped, but this is not overlap. So at which point the actual overlapping will happen? Can anyone say? The structuring element should completely overlap with,
It will do at
the,
many points, no?
yeah. So when you place here, it will completely overlap, right? Here,
Yes.
and here, and here, and here, and here, and here. Is it like this? Here, will it get
No.
overlapped? No, right? And
No.
here, it will overlap. And here,
Yes.
and here, and here, and here, and here, right? So can you see the pattern? Now, this is our actual shape, right? And after erosion, what is the shape? One portion of the input is actually eroded out, right? Is it clear? എല്ലാവർക്കും മനസ്സിലായോ? Gaurav, are you clear with this?
Yes, sir, but I need some more. Like basically, we are saying we are
If the
resizing
structure,
the image or what
no,
it is
not
like.
resizing,
Okay,
the
because
structuring element is there. The structuring
yes,
element is actually doing a filtering process over here. And
okay,
how that filtering is happening? If you place a structuring element, that structuring element should overlap with pixels which are having the same value of that structuring element.
okay,
Now we can actually uh, get those pixels in the output as high where the structuring element overlaps completely. Okay.
okay.
ബാക്കിയുള്ളവർക്ക് മനസ്സിലായോ?
സ്ട്രക്ചറിങ് എലമെന്റും അതും കൂടെ കണക്ട് ചെയ്യുന്ന എനിക്ക് മനസ്സിലാവുന്നില്ല
ഈ
സംഭവം.
സ്ട്രക്ചറിങ് എലമെന്റ് നമ്മൾ ഇവിടെ കൊണ്ട് പ്ലേസ് ചെയ്യുന്നു. ദിസ് സ്ട്രക്ചറിങ് എലമെന്റ്, ഈ സ്ട്രക്ചറിങ് എലമെന്റ് നമുക്ക് ഇവിടെ കൊണ്ട് പ്ലേസ് ചെയ്യാൻ പറ്റുമല്ലോ. ഇവിടെ കൊണ്ട് പ്ലേസ് ചെയ്തൂടെ? ഇവിടെ പ്ലേസ് ചെയ്യാലോ.
പ്ലേസ് ചെയ്യാം.
പക്ഷെ ഇവിടെ സ്ട്രക്ചർ എലമെന്റ് ഇത്രയും പൊസിഷനിൽ റെഡ് ആണ്. അതിവിടെ ഓവർലാപ്പ് ആയോ?
ഇല്ല.
ഇല്ല. അതുപോലെ ഇവിടെ പ്ലേസ് ചെയ്യാലോ നമുക്ക്. അപ്പോഴും ഓവർലാപ്പ് ആകുന്നില്ലല്ലോ.
ഇല്ല.
ഇല്ല. അങ്ങനെ നോക്കിക്കഴിഞ്ഞാല് ഇത് കംപ്ലീറ്റ് ആയിട്ട് ഓവർലാപ്പ് ചെയ്യുന്ന പൊസിഷൻസ് ഏതൊക്കെയാന്ന് നോക്കാം. ഇപ്പൊ ഇവിടെ വെച്ചാലും ഓവർലാപ്പ് ആവില്ല. എവിടെയാ? ദാ ഇവിടെ വെച്ചാലും ഓവർലാപ്പ് ആവില്ലല്ലോ.
എല്ലാ ഭാഗവും
എല്ലാം ഓവർലാപ്പ് ആകണം.
എല്ലാ ഭാഗവും ഓവർലാപ്പ് ആവണം അല്ലേ?
അതായില്ലല്ലോ.
ഇല്ലില്ല.
അപ്പൊ കംപ്ലീറ്റ് ആയിട്ട് ഓവർലാപ്പ് ആകുന്ന ഒരു സ്ഥലം ഇതാണ്. അപ്പൊ ആ പിക്സൽസ് മാത്രമേ ഔട്ട്പുട്ടിൽ എന്താവുള്ളൂ? ഹൈ ആവുള്ളൂ. മനസ്സിലായോ? അതുപോലെ ഇവിടെയും നോക്കിയേ, എല്ലാം ഓവർലാപ്പ് ആവുന്നില്ലേ? ഓക്കെ.
അല്ല, അവിടെ നമ്മൾ ആ ബ്ലാക്ക് ഡോട്ടും റെഡും ഇട്ടില്ലേ? നേരത്തെ ഓവർലാപ്പ് ആയപ്പോ എല്ലാത്തിലും നമ്മള് ബ്ലൂ ഡോട്ടും ബ്ലൂ സർക്കിൾ ചെയ്തില്ലേ സാറ്? മേലെ നമ്മൾ ഓവർലാപ്പ് ആയതുകൊണ്ട് റെഡിൽ തന്നെ കിടക്കുമല്ലായിരുന്നോ? ഈ രണ്ട് പോർഷൻ ഇല്ലായിരുന്നോ ഓവർലാപ്പ് ആയതും?
ഇല്ല, മിസ് ചോദിച്ചോ മനസ്സിലായില്ല.
ആ സർക്കിൾ ഇട്ടില്ലേ, ഒരു ബ്ലൂ കളറിൽ ഷെയ്ഡ് ചെയ്തില്ലേ സാറ്? അതും ആ റെഡും തമ്മിലുള്ള ഡിഫറൻസ് എന്താ?
റെഡ് ഒറിജിനൽ ഇൻപുട്ടിലുള്ളതായിരുന്നു റെഡ്.
പക്ഷെ നേരത്തെ ഓവർലാപ്പ് ആയപ്പം അവിടെ നമ്മള് പിന്നെ തൊട്ട് മുന്നത്തെ സ്പേസിലെ
ഇവിടെ ഒന്നും ഇട്ടില്ലല്ലോ നമ്മള്. ഇവിടെ അല്ലേ ഇട്ടുള്ളൂ.
അവിടെ ഇപ്പൊ എല്ലാം ഓവർലാപ്പ് ആയി എന്ന് പറഞ്ഞാല്
ഈ ഇവിടെ ഓവർലാപ്പായി ഇതുമായിട്ട്, ഇത് ഓവർലാപ്പായി ഇതുമായിട്ട്, ഇത് ഓവർലാപ്പായി ഇതുമായിട്ട്.
അപ്പോഴ് ആ ലെഫ്റ്റിലിട്ട റെഡില്ലേ, അതിൽ എന്തുകൊണ്ട് സാറ് ബ്ലൂ മാർക്ക് ആ സർക്കിൾ ചെയ്തില്ലാന്ന് ചോദിച്ചത്?
അതായത് സെന്ററിൽ മാത്രമേ, നമ്മൾ ഈ സ്ട്രക്ചറിങ് എലമെന്റിനെ ഒരു സെന്ററിലാണല്ലോ കൊണ്ട് പ്ലേസ് ചെയ്യണേ. ആ സെന്റർ മാത്രമേ നമ്മൾ മാർക്ക് ചെയ്യുള്ളൂ. അടുത്ത മൂവ് ചെയ്ത് റൈറ്റ് വരുമ്പോഴാണ് ഇത് മാർക്ക് ആവണേ.
അത് സെന്ററിൽ വരുമ്പോ അല്ലേ?
അതെ.
അതാണ് എനിക്കത് ക്ലിക്ക്
സെന്ററിൽ വരുന്ന പിക്സൽ മാത്രമേ എന്ത് ചെയ്യുള്ളൂ?
സർക്കിൾ ചെയ്ത്
സർക്കിൾ ചെയ്യുന്നുള്ളൂ. ഓക്കെ അല്ലേ?
ഓക്കെ സാർ.
Yes.
One question.
Yeah.
For erosion, this structure matrix is always same, right?
No.
Or
that
it
I'm going
can
to
change?
tell you now.
Okay.
If this is the structuring element, can anyone say what all pixels will get? This is the structuring element. This is the center of the structuring element. we know obviously these regions will not get marked, right? I can start with here. Will it get marked in the output? If you place the center of structuring element at this point, will it get marked or
Sir,
not?
I cannot see your cursor somehow, so I am not able. Okay.
See,
Yeah,
see.
I can see it now.
Yeah.
Got it. No, sir.
No. Here,
No,
here,
no. Any
here,
top will be no. Yes.
here,
No.
here,
Yes.
yes. Here,
Yes.
here,
Yes.
yes. Here,
No.
here,
Yes.
here,
Yes.
here,
Yes.
here,
Yes.
here,
Yes.
here,
No.
here,
Yes.
here,
Yes.
here,
Yes.
here,
Yes.
here,
Yes.
here, yes.
Yes.
Here, no.
No.
Here, no. Here, no, right? See, the same erosion is happened, but since the structuring element is different, the eroded shape is something like this now, right? Is that clear?
Okay. And
Okay.
probably just how this structuring
ആ,
element is defined somewhere.
Yeah,
നമുക്ക്
Like
ഏത്
usually,
എങ്ങനെ വേണേലും എടുക്കാവോ ഈ സ്ട്രക്ചറിങ്?
usually നമ്മളൊരു symmetric shape consider ചെയ്യുക. That is actually, this is what we are calling as a morphological cross. Okay. So this is the most appropriate structuring element.
okay.
Okay. So,
Suppose we have more than one object,
okay.
but they have some space. So the same procedure, right?
Yeah, the same procedure. We can actually see that. See here, in this example, you can see the width of the stalk is actually getting reduced, right? Because it is eroding it, right? And we can repeat this process by making these iterations different. So it will first do the erosion. Again, if you do this erosion again the width is getting reduced, right? So that is the number of iterations. Okay. And dilation is simply opposite to erosion. What is this? What happened here? Dilation is simply opposite to erosion. So what happening in dilation is that, see,
Sir, in the previous case, I just tried iterations for it changed to yellow and some blue something color
yellow,
for
yeah,
erosion.
why it is yellow and blue, I mentioned while plotting this. Okay. While plotting, we can use this option, C map equal to gray.
No, for erosion alone, when I'm doing iterations in the beginning, it was the sample text here that content was getting eroded. However, when I increase the iterations to 4, the color, the background color also changed.
Background color in the sense,
I tried with iterations 4.
yeah,
I
like
got
this,
some, yes.
because that erosion operation is not at all possible there. After
Okay, the
two
object
erosion,
itself has gone.
yes,
Is it? Okay.
yeah. Okay. So the dilation operation is again, see what is happening is if the structuring element is placed somewhere, okay, if one of the part is actually getting overlapped, okay, one of the part is getting overlapped, then what will happen? It will be marked in the output. Are you getting it?
You don't have to fully cover that structuring element.
Yeah, that is.
So all points will get marked, no?
No, like, see, if you place, I'm showing you the output. If you place here, this is the structuring element, okay? If you place here, will it get overlapped at any point?
Cannot see your cursor actually.
Here. Here.
No.
No, it will not get overlapped, right? And what about here? Here?
No.
No. Here? One
No.
position is getting overlapped, right?
Yes.
Then we can mark this. Here also one point is overlapping. Here it is overlapping, and in all other points not happening, right?
Hmm.
And what about here? It will work.
Yes.
It will obviously work, right?
Yes.
And what about this? Work. This will work. Anyway, here this, 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 this. And what about this? No, right?
No.
Here,
Yes.
here,
Yes. Yes. Yes.
here,
Yes.
here, 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 here.
Yes.
No, here, right?
Oh, yes.
Here, yes, right? See overall what happened to the shape?
Enlarged.
It is dilated.
It is getting dilated. Is that clear?
Will the shape remains the same always?
Yeah, for this particular structuring element, the shape will be preserved. But
Okay.
according to different structuring element, it will change,
But then that image will get
distorted.
yes.
Yes. So that is how it's happening here. See, here what happened is we have dilated the output. Okay, right? And we can actually have different kind of morphological operations. See here, you can see this, right? The original image, the dilated one, the eroded one. Okay. And how this is happening? Internal boundary. Internal boundary. The internal boundary can be created by, see what is happening. I'm just placing the code. Okay. I have an eroded image and the dilated image, right? So I'm simply plotting image dilated minus image. What will happen? See, dilated minus image, original image. So we can actually get the dilated region. Comparing to the original one, which all part are getting dilated. And this is what we are calling as outer boundary. Okay, outer boundary. And if you do this by image minus eroded, image minus erosion. Okay. This is called as internal boundary. Okay, internal boundary. Okay. And similar to this, you can actually do the morphological gradient. Gradient is nothing but dilation minus erosion. That is actually called as morphological gradient.
സാർ കോഡൊന്ന് ആ കോഡൊന്ന് ടൈപ്പ് ചെയ്തോട്ടെ, അല്ലെങ്കിൽ ഒന്ന് ചാറ്റ് ബോക്സിൽ ഇട്ട് തരാണെങ്കിൽ.
And we can do we can do a lot of operations like this. Morphological something called original erosion dilation, morphological opening, morphological closing is there. Okay. If we are using opening, what will happen is a small bridge. If there are small bridges appear, that will get disconnected. That is the process of morphological opening. If we are doing closing, see small black gaps will get closed. Okay, that's the effect of opening and closing. So if this is the original image, while opening, this edges will be removed. By closing, the black will be closed. Okay, so this kind of opening, closing operations are also there. There are direct function for this, and with erosion and dilation itself, we can do this. We have equations for this opening and closing. I can show you. See, these are the function. Morphological opening can be there. Closing will be there. Yeah, this is the understanding. See, if you do the dilation first, then the erosion, it will be closing. Okay, first do dilation on the input image, then do the erosion, it will be closing. If you do the erosion first, then dilation, then it will be opening. Then edge extraction algorithms, a lot of things are there. So, hope you understood, right? What is erosion, what is dilation, the external boundary, the internal boundary, opening and closing. So I'm going to show you how these things are actually used particularly. Okay. So the next operation is actually thresholding. Thresholding is nothing but we fix a particular pixel value, then all values below that pixels will be mapped into 0 and below that to 255. Okay. So different types of thresholding is there. See, this is the original image. The first one is the binary thresholding. There we are taking 127 as a threshold value. So all values greater than 127 will be mapped to white. All value less than 127 is mapped to what? Black. That is what we are seeing. And the inverted one. That is, all value greater than 127 is mapped to 0, and all value less than 127 is mapped to white. That is threshold binary inverted. Okay. Then a truncated thresholding is there. Okay. It will automatically identify a value. Then this is a kind of normalization to 0, then to 0 inversion, different type of thresholding. We usually use this function, that is binary inversion, for many of the experiments. Okay. And sometime there is something called edge detection. And there are different algorithms for detecting edge. The first one is actually called as Laplacian edge detection is there, Sobel edge, canny edge, different types of edge detections are there. We have different, we have direct function for detecting the edges. So this will be like this. The original image, the canny edge detection is like this. Sobel X, Sobel Y, Laplacian is there. So in different ways, we can actually highlight the edges. Okay. So all these things are actually coming under the image processing techniques, and there are a lot of other techniques too, but these are all the different useful things while doing the machine learning pipeline. So we started with loading the images, saving the images, cropping the images, displaying the images, and then resizing the image, rotating it, writing a text on it, the different color maps, then the morphological, how to convert between different color maps, the morphological operations, histogram equalization, then dilation, erosion. Now we are going to discuss about image feature extraction. So this is the application of what we have learned so far and how this can be used as a image descriptor. Okay, image descriptor is nothing but how an image can be represented as a set of values. Okay. Now see, we can directly use the pixel values itself as image descriptors. See, just load the image, convert that numpy array into a single array. Then you can use this ravel function for representing it. So this image is now represented as a vector of pixel values. Okay. So this is the first kind of feature representation. The second one is, see, we use histograms to represent it. Okay. How can we do that? We will consider the input image. Okay. We will use the, see, this is the function. Okay. And we have to give the input. We have to give the minimum value. Okay. Then the maximum, the threshold, the maximum value, and the range. So it will calculate the histogram of this particular image. So how many values will be here? How many values will be, can anyone tell me how many values will be here? How many values? There will be 255 bins. This particular 50 represents how many black pixels? 50 black pixels, which is represented as 0. How many pixels? 1 pixels. How many 2 pixels? How many 3 pixels? How many 4 pixels? How many 255 pixels? That is actually plotted over here. Okay. So this is how we are representing image as a histogram. So every image can be converted into what?
Sir, ഇപ്പൊ പറഞ്ഞ ഒന്നുകൂടെ ഒന്ന് പറയാം, മനസ്സിലായില്ല.
That is, for a particular flower image, there will be pixels marked as 0, there will be pixels marked as 1, there will be pixels marked as 2, like 255, till 255 will be there, right? So this is represent 50 means there are 50 pixels in the image flower, okay, which is having the value 0.
Okay.
There are 5 pixels in that flower image which is having the pixel value 1.
Okay.
Right. So likewise, what is this? 3. There are 3 pixels
having 255.
having the pixel value 255. Clear?
Okay.
Okay. Now, the RGB values as image descriptors. You can see the difference here. See, I'm taking an apple image, okay, a strawberry image, and image of grapes, okay. So what I'm doing is, I'm just loading the apple, strawberry, and grapes. Then I'm converting BGR to RGB, okay, BGR to RGB. Then I'm taking the mean of all pixels, okay, mean of all pixels. Then there will be 3 channels, mean of first channel, mean of second channel, mean of third channel. It's actually printed as features. So on plotting this, can you observe anything? Are you able to observe anything? For the first 2 images, the average pixel values are somewhat very near, right? 1, 218, 210, 167, 165, 159, 152, right? But for the third image, what happened? The pixel values are, the average pixel values are different, right? So if you want to do a color-based classification, every image can be converted into its corresponding average pixel value. So every image will be converted into what?
RGB values, no?
RGB, the average of RGB values. Is that clear? So if you are doing, yeah.
Sir, this is only for color, correct? Not
Yeah,
for anything else.
only considering color.
Color. Okay, makes.
Yeah, that is why it is called as a color descriptor. Okay,
Then if the size is more, the value will be different, no?
No, because we are
If
taking the average.
apple size is bigger and strawberry size is smaller. Oh yeah,
No,
we are taking
the average of all pixels, right?
Okay.
So whatever number of pixels it is, it will be averaged and finally mapped into 3 values. Okay. And see, these are all these are 2 images which is having the same content, right? What is the difference you feel here? The content is same, the colors are, the brightness is different, right? But if you simply take the color values, what will happen? If you simply consider the mean of pixel values, you can see that their values are entirely different, right?
Yes.
Right? The values are entirely different. So we need a measure which is independent of the light intensity. Okay, which is independent of the light intensity. And we have seen that there is a color space called lab, where the first component of that color space is representing the light, right? So if you first convert this image into lab, BGR to lab, and then take the average. You can see that only the color component is different. The other two components are similar, right? Is that clear? So you can avoid these two components if you want to take a light invariant feature. Okay, light invariant feature. Hope it is clear, right?
Actually, that
Yeah.
average still has some confusion, because when you take the average of that row or column,
Ah.
the value that depends on that size, as one of the participant mentioned, that it will depend on the size of the object that is encoded in it, right?
Ma'am, what is the meaning of average itself? It is always tending to the majority, right?
Yes.
So in these two images, what is the majority color?
Correct.
Red. So by taking the average of these two images, it will always somehow nearer to the what? Red color. That is why this R value is having more.
Actually, this is a very simple image, but when you have a real image,
Yeah.
because I am thinking about galaxies and all, you have so much of
Yes.
space in between, and you have light coming from only some small regions. So when you take the average, I don't know how you'll be able
Yeah,
to.
so in that case, what we have to decide is color is not enough
Okay.
for the decision making,
Okay. So okay. So right
right?
now, this is a problem where you are trying to identify a fruit based
Or
on color.
distinguish fruits based on color,
Okay.
right? There are
Yes.
some region, if you get a satellite image, suppose if you want to classify some wetlands, vegetated lands, seas, uh, or some dry lands, color is enough, right?
Yes.
Okay. Yeah. So
Then at that time, maybe you can remove the background and you can just focus on that.
yes, exactly. In that pipeline, we can remove the background.
Okay, sir. Thank you.
Yeah.
സാർ നമ്മുടെ ഇന്റൻസിറ്റി വേരിയേഷൻ വരുന്ന ഈ എക്സാമ്പിൾ പറഞ്ഞല്ലോ,
ആ
ഇവിടെ നമുക്ക് ഈ ഹിസ്റ്റോഗ്രാം ഈക്വലൈസേഷൻ യൂസ് ചെയ്ത് കഴിഞ്ഞാൽ രണ്ട് ഇമേജും സിമിലർ ആയിരിക്കില്ലേ?
ഹിസ്റ്റോഗ്രാം എടുത്തു കഴിഞ്ഞാലാണോ ഹിസ്റ്റോഗ്രാം ഈക്വലൈസേഷൻ ആണോ ഉദ്ദേശിച്ചത്?
ഹിസ്റ്റോഗ്രാം ഈക്വലൈസേഷൻ രണ്ട് ഇമേജിലേക്കും കൊടുത്തു കഴിഞ്ഞാൽ ആ ഒരു സ്പ്രെഡ് ഈക്വൽ ആയിരിക്കുമല്ലോ, ഓൾമോസ്റ്റ് സെയിം കണ്ടന്റ് ആയതുകൊണ്ട്.
പക്ഷെ ഇത് ഗ്രേ സ്കെയിൽ അല്ലല്ലോ.
നമുക്ക് അത് സെപ്പറേറ്റ് ചാനലിൽ അങ്ങനെ ചെയ്യാൻ പറ്റില്ല.
നമ്മൾ യൂഷ്വലി ചെയ്യുന്ന മറ്റേതിലാണ്, ഗ്രേ സ്കെയിലാണ് ഹിസ്റ്റോഗ്രാം ഈക്വലൈസേഷൻ ചെയ്യുക.
Okay.
Yeah. Okay. Now, sometime the shape is actually matters. See, you can see these images of brain tumors. Okay. So these are two brain tumors. Okay. That can be classified into malignant and benign. Okay. So this is the malignant one and this is the benign one, right? So how we can actually do that? Okay. So how can we extract features from this that represent the shape and size? Okay. So for that, first I'm converting it into gray. See, after doing the thresholding, you can see that the high intensity regions are mapped into what? White, and the low intensity is mapped as black. Okay. And these are all the noises, right? So as I already said, the opening operation, if you apply opening operation here, what will happen? All that small patches will be removed and all the noises are now removed. Is that clear? Right? All the noises are now cleared. now we can actually get the region of interest alone, right? Now I need some measures that represents the size of this. For that, I'm considering a particular feature of this thing called contour. Contour is nothing but it is a collection of points which marks the boundary of this, So I'm finding the contour of T underscore image 1 and finding the contour of the second image 2. Okay. After getting the contour, what I'm doing is I'm calculating the area that inside the contour. For that, contour area function can be used. So the contour 1 is applied for contour area. Then contour 2 is applied on contour area. Then I'm keeping two lists, F1 and F2. To F1 and F2, I'm appending area 1 into F1 and area 2 to F2. Also, the perimeter is also a measure that represents the size, right? So I'm calculating the arc length of contour 1 and arc length of contour 2. So we got two features. First one is the area and second one is the perimeter. So it is evident that for the first benign tumor, it is 265 the area and 65 is the perimeter. And for the second one, area is 2202.5 and the perimeter is 180. It is very distinguishable from that measures itself. But I want to look into some more measures. What I am doing is I am taking the bounding rectangles. What is this? Bounding rectangles. After getting the images, I am simply calculating the bounding rectangles from contour 1 and bounding rectangles from contour 2. Then that rectangles are xy, wh. That is the starting point, xy and the width and height of the rectangle. That width and height is an important thing, right? Width and height. That width and height is representing the size of it. So I'm adding width and height as a feature. And for the second image also, I'm calculating the width and height and adding it in the feature. Okay, right? So again, my features are now see the 16, 22, 23 is the width and height. And for the second image, it is 53 and 51. And one more feature I can take is instead of calculating the contour rectangle, I'm calculating the contour. I'm calculating the minimum enclosing circle that encloses the contours. Okay. So from here also, the radius of the circle, the minimum enclosing circle is actually giving us the idea of the size of the tumor, right? So here what I'm doing is I'm taking the images of calculating the minimum enclosing circle, calculating the center and the radius. Then I'm adding the radius as a feature to the F1. Okay. And plotting that circle. Here also, for the second image also, we are doing the same. And we added the feature. Okay. Now, if you print this F1 and F2, you can see that the first image is represented using a 5-dimensional vector and the second image is also represented using a 5-dimensional vector. And from the values of that vectors itself, it is very evidently clear that we can distinguish or we can classify the first image as a benign one and the second one as a malignant one. Is that clear? Is that clear? Okay.
യെസ് സാർ. പക്ഷെ ഇങ്ങനത്തെ ഒരു കേസിൽ ഈ രണ്ട് ഇമേജും ഒരേ സൈസുള്ള ഇമേജ് ആയിരിക്കണ്ടേ? അങ്ങനെയാവുമ്പല്ലേ അത് ക്ലിയർ ആയിട്ട് കിട്ടുള്ളൂ?
വേണ്ട, നമ്മൾ അതിനെ ആദ്യം തന്നെ എന്ത് ചെയ്യുന്നുണ്ട്? ഒരേ സൈസിലേക്ക് നോർമലൈസ് ചെയ്യുന്നുണ്ട്. നോക്കൂ, ഫസ്റ്റ് ഇമേജ് രണ്ടും എടുത്തു കഴിയുമ്പോൾ നമ്മൾ അതിനെ 150 സൈസിലേക്ക് മാറ്റുന്നില്ലേ?
ഓക്കെ ഓക്കെ ഓക്കെ
ഓക്കെ. സോ ദിസ് ഇസ് അബൌട്ട് ദ സൈസ്. ഇനി ഷേപ്പ് ആണ് നമുക്ക് മാറ്റർ എങ്കിൽ വി ക്യാൻ കൺസിഡർ ദിസ് ഷേപ്പ്. പക്ഷെ ഇവിടെ നിങ്ങൾക്ക് നോക്കിയാൽ കാണാം രണ്ടും ഹ്യൂമന്റെ ഷേപ്പ് എടുത്തു കഴിഞ്ഞാൽ സംഹൗ സിമിലർ ആണ്. കാര്യം രണ്ടും ഏകദേശം സർക്കിൾ പോലല്ലേ ഇരിക്കുന്നത്. സോ ഷേപ്പ് വോണ്ട് ബി എ ഗുഡ് മെഷർ ഫോർ ദിസ് കേസ്. മനസ്സിലായോ? ഷേപ്പ് നമുക്കൊരു നല്ല മെഷറായിട്ട് പറയാനായിട്ട് പറ്റില്ല. സോ വാട്ട് വി ക്യാൻ ഡു ഇസ്, ഇങ്ങനെ ഷേപ്പ് മാറ്റർ ആവുന്ന കേസസിൽ
Sir,
shape based.
sorry, can you repeat what?
Yes.
Sorry.
See, if there is a measure called hue moment, okay, but if you calculate the hue moment of both the images, it was somehow very similar. Okay, somehow very nearer. Why? Because
Okay.
because these two shapes are somewhat similar, right?
Circle. Yeah. Okay.
But for this case, for distinguishing between K and S, okay, K and
Yes.
S, what happened? The shape will be different, right?
Yes. Correct.
In that case, we can actually take the hue moments. See, this hue moment and this hue moment is entirely different, right? But hue moment for all the S is somewhat very, very nearer to. So if you're concerned with shape, you can actually use that. Okay. So suppose you want to do a leaf classification. Can you tell me which feature will help us?
Shape.
The shape, right? So in that case, what we can do? We can consider the
Hue moment.
hue moments as a feature for this. Okay.
In the other
Then-
case, but the problem is if the tumor is small and it still means in the beginning of of the disease or the cancer, if it is the beginning, you cannot identify, right? Because the
Yes,
size
yes.
will be small.
Yes. So it should be evident for the human eye. We cannot actually do any kind of
Okay.
magic with that. Yeah. And sometime, see, if suppose you want to classify the agriculture land and forest. Okay, agriculture land and forest. Okay. These are the two images. Suppose you have a drone, and through by capturing the image through drone, I want to classify whether it is a agriculture land or a forest. So what is the clue? Will color help for
No,
agriculture
sir.
land and
No, sir.
forest?
It will
No.
be green.
Shape,
No. Again.
shape,
No.
size.
Sir, it will be intensity mostly, my understanding.
Intensity, but if the sunlight varies, that will change, right?
Yes, but forest will be more dense, like more dense color in green, so it might be this.
If you look into a paddy field in Kerala,
Okay.
it will be more green.
Okay.
So
Or
the
extract any pattern.
pattern, the clear word is that is what I'm intending. That is the texture, right? Even if the color is same, see the forest versus paddy field. See? So you can see a difference right here.
Yes, sir.
See,
Got
if you look into a forest, it will be like this. But if you look into a paddy field, it will be like this, right?
Yes, correct.
So what is actually different there? the texture is there. Everything is actually green and all, right? So the texture difference can be tracked with a feature called GLCM. Okay, gray level co-occurrence matrix. Okay, so statistical method for image texture analysis. Okay, sometime the texture of the galaxies will be different, right? If you look
Yes,
into
yes,
some
yeah. Actually,
images,
sometimes some may be having spiral arms.
yeah.
Those kind of
So
structural differences there.
yeah, that can be handled with this. Okay. So what I recommend is that this is how the traditional image processing and machine learning stuffs need to be combined. Okay. And we cannot mug up with all the feature extraction techniques, but there is a textbook, image feature extra. I had the copy of that, PDF of that. Computer vision. But now I don't have, I lost that. But there's a good text. Yeah, this text. Can you see that? Image feature extraction and image processing for computer vision. This is a very good text. They explain a lot of feature extraction techniques for different use cases. So if you really want to do some research on traditional images and machine learning, you can actually refer this textbook. Okay. So I think the PDF of this text is available. If you have this, just go through this. This will be a very helpful one. As I said, if you want to do these things in an easy way, you can simply go for deep learning. There is no need of looking into this features, feature extraction, pre-processing and all. But for the learning purpose, I would say try to do things with the image processing and machine learning. If you do experiments with that, you will be having, definitely you will be having an upper hand. And then it is very easy to explain things to the students and think in a particular way. Okay. So these are all positive things. These are all negative samples. So you can actually look into this, how these things are actually distinguished. So whenever it becomes complex, you are not able to find a proper this proper feature for distinguishing this, then definitely you just go for what? Deep learning. But if you have a proper idea of how these things are getting classified by considering different features, you can experiment with the machine learning things. Then you can go for what? Deep learning. Okay.
Now you have two techniques. So which one is, means we know the structure or we know the feature, but if deep learning is giving you a better classification, then we will go for that, right? So which one is better?
Yeah, ma'am, for developing an application, okay. Suppose if you want to build a project, you can actually go with that. Okay. But if you want to come up with a novel thing, okay, in different aspect, we can actually look, evaluate our method, right? So if you really want to come up with a novel thing, simply using deep learning is actually not much contributing to the research. So in that case, if you are able to find out a proper features that explains the difference between different classes of images, and using that features, if you are able to do a better classification, a comparable result is getting, then you can actually go for what? Machine learning.
Okay.
we always recommend to use machine learning because the machine learning is very lightweight and it is actually more explainable. Okay. So what we usually recommend is if you can build a machine learning model with explicit features and the result is very much comparable with a deep learning model, always go for machine learning. Okay.
സാർ ഒന്ന് റിപ്പീറ്റ് ചെയ്യാം.
നമുക്ക് ഒരു മെഷീൻ ലേണിംഗ് മോഡല് എക്സ്പ്ലിസിറ്റ് ഫീച്ചേഴ്സ് വെച്ച് നമ്മൾ കണ്ടെത്തിയ എക്സ്പ്ലിസിറ്റ് ഫീച്ചേഴ്സ് വെച്ച് നമുക്കൊരു മെഷീൻ ലേണിംഗ് മോഡൽ ബിൽഡ് ചെയ്യാൻ പറ്റും. അതിന് ഒരു ഡീപ്പ് ലേണിംഗ് മോഡൽ തരുന്നതിൻ്റെ ഏകദേശം വളരെ അടുത്ത് തന്നെയുള്ള ഒരു പെർഫോമൻസും ഉണ്ടെന്നിരിക്കട്ടെ, നമ്മളെപ്പോഴും മെഷീൻ ലേണിംഗ് ആണ് പ്രിഫർ ചെയ്യുന്നത്. കാരണം
main reason is because machine learning models are more explainable, right?
Machine learning models are more explainable
Expl-
as well as it is taking
Lightweight.
less resources
Yeah,
for the
lightweight.
training.
Yeah, okay. Makes sense. Thank you.
Clear ആയോ?
സാർ നമുക്ക്
Yes, sir.
പ്രോപ്പർ അതായത് ഫുൾ ട്രെയിനിങ് കഴിഞ്ഞിട്ട് ആ മോഡൽസ് ഇവാലുവേറ്റ് ചെയ്യുന്നതിന് പകരം അതിന് മുമ്പ് നമുക്ക് ഡിസൈഡ് ചെയ്യാൻ പറ്റും ഒരു ഡാറ്റ സെറ്റ് കണ്ടിട്ട് നമുക്ക് ML ആയിരിക്കോ അതോ ഡീപ്പ് ലേണിംഗ് ആയിരിക്കോ സൂട്ടബിൾ എന്നുള്ളത്?
ഡെഫിനറ്റ്ലി പറയാൻ പറ്റുമല്ലോ. കാര്യം ഇപ്പൊ ഒരു ഞാനിപ്പോ ചോദിക്കുകയാണ്, യു ഹാവ് an images of apple and you have an images of banana. ഓക്കെ, ദൈവത്തെ ഏതായിരിക്കും പ്രിഫർ ചെയ്യുക?
ഡീപ്പ് ലേണിംഗ്.
എന്തുകൊണ്ട് ഡീപ്പ് ലേണിംഗ് പ്രിഫർ ചെയ്യുന്നത്?
അവിടെ ഒരു ഫിക്സഡ് പാറ്റേൺ ഇല്ലാത്തതുകൊണ്ട് മീൻസ് നമുക്ക് ഡയറക്ട്ലി
ആപ്പിളും ബനാനയും തമ്മിലോ?
നമുക്ക് ഡയറക്ട്ലി ക്യാപ്ചർ ചെയ്യാൻ പറ്റുന്ന ഫീച്ചേഴ്സ് കുറവാണ്.
ആപ്പിളും ബനാനയും തമ്മിലൊന്ന് ആലോചിച്ച് നോക്കി.
അതില് മെഷീൻ ലേണിംഗ് പോരെ?
ഇമേജ് ആയതുകൊണ്ടാണ്.
ഇമേജ് ആകുമ്പോ ആപ്പിൾ ഇസ് ആക്ച്വലി സംഹൗ ഒരു റെഡ് ഷെയ്ഡിലായിരിക്കുമല്ലോ വരിക. ഈ എക്സെപ്ഷൻസ് വേണ്ട കേട്ടോ, ലൈക്ക് തിങ്ക് ചെയ്യണ്ട. എല്ലോ ആപ്പിളൊക്കെ ഉണ്ട്, ബട്ട് ഒരു കാറ്റഗറി. അല്ലെങ്കിൽ ഇപ്പൊ നമുക്ക് ഒരു റോബസ്റ്റോയും ഒരു പൂവമ്പഴവും തമ്മിൽ ക്ലാസിഫൈ ചെയ്യണം. നമുക്ക് അവിടെ ഇമേജസ് ഡയറക്ട്ലി എടുത്ത് നമുക്ക് ചെയ്യാൻ, മീൻസ് കളർ എന്ന് പറയുന്ന ഫീച്ചർ ഡയറക്ട്ലി എടുത്ത് ചെയ്തൂടെ? അപ്പൊ ആ കേസിൽ നമുക്ക് എന്ത് ചെയ്യേണ്ട ആവശ്യമില്ല, ഈ പറയുന്ന
ഡീപ്പ്
ലേണിംഗിലേക്ക് പോകേണ്ട ആവശ്യമില്ല.
ഓക്കെ.
അത് നമുക്ക് ഇൻപുട്ട് ഇമേജസ് ഇപ്പൊ ലീഫിന്റെ നേരത്തെ ക്ലാസിഫിക്കേഷൻ ഞാൻ പറഞ്ഞില്ലേ, ലീഫിന്റെ ചെയ്യുന്ന സമയത്ത് ഈ ഹ്യൂമമെന്റ് എന്ന് പറയുന്ന ഒരു സാധനത്തെ പറ്റി നമുക്ക് അറിയത്തില്ലെങ്കിൽ നമുക്കത് കോംപ്ലക്സ് ആയിട്ട് തോന്നും. റൈറ്റ്? അതിനാണ് നമ്മൾ എപ്പോഴും എന്ത് വായിക്കണേ, ലിറ്ററേച്ചേഴ്സ് വായിക്കുമ്പോൾ ആ ലിറ്ററേച്ചേഴ്സിൽ ഉപയോഗിച്ചിട്ടുള്ള മെത്തേഡുകളെ നമുക്ക് മനസ്സിലാക്കിയെടുക്കാനായിട്ട് പറ്റും.